Welcome to this video on the rules of probability. This is one of several videos in a short course on probabilities and random variables posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. Suppose you are involved in the design of a bridge, or perhaps a high-rise building tower. As an engineer, your primary concern is to prevent failure of the structure in, say, the next 50 years. Or maybe you are concerned about the failure of the functionality of a community and a portfolio of structures in an impending earthquake. Or perhaps you are simply worried about the potential failure of a new phone that you just purchased, so that you can decide whether to purchase insurance. For most engineered devices and structures, there is the possibility that it will fail. However, there are unavoidable uncertainties in the capacity of the structure to sustain loading, and there is even more uncertainty about what kind of loading that will occur in the lifespan of the structure. This is why engineering is essentially decision-making under uncertainty. And engineers always need to make decisions about big and small design details. That is what separates an engineer from a scientist. A scientist can study a subject matter forever, while the engineer must make decisions. As an engineer, you may be explicitly faced with such decisions only for large or special engineering projects. That is because code committees have made the decisions under uncertainty for us, in the form of building codes and design standards for different materials. Whether you are working on a special project that is not covered by codes and standards, or you are the member of a code committee, you will find that the decisions are made in a back-and-forth procedure between design and analysis. Trial designs are established, followed by analysis to reveal whether the design is acceptable. Many of the notes posted at terje's Toolbox address analysis instead of design. And every analysis employs models and methods. In the notes and videos on basic structural analysis, you will see the same pattern. The models in basic structural analysis are idealized trusses and frames with well-defined support conditions, such as pin and roller supports. Conversely, the methods in basic structural analysis include the stiffness method, the flexibility method, and the moment distribution method. In contrast, you are now watching a video on probabilistic analysis. For many students, this means we have taken the step from undergraduate education to graduate-level education. It also means that we are trying to address the uncertainties that are brushed under the carpet in basic structural analysis. It means that the models are now random variables, functions of random variables, stochastic processes, etc. It means that the methods are probabilistic, as you will learn about in this short course on probabilities and random variables. Additional methods, referred to as reliability methods, are the subject of another short course on structural reliability, posted at terje's Toolbox. The result of such kinds of analyses is often a probability that a structure will fail during some time frame. The decision that we are seeking might be made by comparing that probability to a target probability that should not be exceeded. This is the predominant approach when code committees decide whether a design is suitable. Another approach is to compare the risk associated with different decisions. Risk is defined as cost times probability. One decision may have a low cost of failure, but when that cost multiplies with a high probability of failure, then the risk may be substantial. Another decision may be associated with a high cost of failure, but have a comparable risk to the previous case because the probability of failure is small. In summary, engineers use probabilities to compare with target values, or to multiply it with the cost of failure in order to compare the risk of different design decisions. In short, probabilities are used to make decisions under uncertainty. How do we express a probability? This slide evolves around a failure probability, P of f, or simply Pf, with value 10 to the power minus 3. What are valid ways in which to express that probability? Clearly, we can simply say 10 to the power minus 3. How about saying that Pf is 1 over 1,000? Sure, that works well, because that is exactly what 10 to the power minus 3 is. Can we say 1 in 1,000? No, that is a mistake. By saying 1 in 1,000, we imply that there are repeated experiments occurring, with failure occurring in some of them. By saying 1 in 1,000, do we mean that one or more failed in 1,000 experiments? Or do we mean that one and only one fails in 1,000 experiments? As you can hear, the expression 1 in 1,000 is not well defined. Moreover, to find the probability of failure in one or more experiments, we must first learn about probabilistic models that govern such experiments. If the experiments are independent, then they are called Bernoulli trials, which we learn about in another video on terje's Toolbox. Can we say 1,000 to 1? This is close to acceptable because we can use odds to express a probability. The expression 10 to 1 or 1,000 to 1 are valid odds. However, none of them are expressing the probability that is 10 to the power minus 3. As we will see on the next slide, you can say 999 to 1 and even 4,995 to 5 to express this probability, but not 1,000 to 1. How about saying 0.1% chance? Yes, it is valid to use chance to express a probability, and this version is correct. To say that the probability 10 to the power minus 3 means 0.1% chance is correct. How about equating this probability to a reliability index of 3? This is a preview of the short course on structural reliability posted at terje's Toolbox. The concept of a reliability index is covered there, and some engineers think that a probability of 10 to the power minus 3 is the same as a reliability index of 3. To use the power in that way is incorrect, although it is an okay approximation for the number 3, but not for other failure probabilities. The next slide will explain why 3.09 is the correct reliability index for this particular probability. The one conclusion you should take away from this slide is that a probability is essentially a number between 0 and 1. Now to a brief explanation of odds and the reliability index. Odds use the preposition to. You can say that the odds are n to m, where n and m are numbers. The formula that links n and m to the probability is shown here. It is common to let the number m be 1, so that odds are expressed as something to 1. In that case, this formula shows how to obtain the number n if you substitute 10 to the power minus 3 for the probability. You will get that n equals 999. This explains the number on the previous slide. If you let m be 5 instead of 1, then you will get that n equals 4,995, again explaining a number that appeared on the previous slide. The concept of a reliability index is outside the scope of this short course on probabilities and random variables. However, it is a valid way to express a failure probability. In the course on structural reliability, we will learn that the failure probability is linked with the reliability index via the standard normal cumulative distribution function, denoted by the capital Greek symbol phi. The failure probability is phi with the negative reliability index, beta, in the argument. Conversely, the reliability index is expressed in terms of the inverse standard normal cumulative distribution function, as shown here. For a failure probability equal to 10 to the power minus 3, you will get a reliability index value of 3.09. This explains the value given on the previous slide. Target failure probabilities around 10 to the power minus 3 or 10 to the power minus 4 are reasonable values in modern structural engineering. On the next slide, we wrap up the introduction of the concept of probability. There are two schools of thought on what a failure probability means. Simply speaking, one school of thought considers the probability as the relative frequency of occurrence in repeated trials. This works well in classical statistics, where we make inference based on a number of observations. This understanding of a probability is reflected in this formula, where NE is the number of occurrences of an event E in n trials. According to this school of thought, which is often referred to as classical statistics, the probability is entirely objective and empirical and based on observations. In contrast, the Bayesian school of thought is more appropriate in engineering applications where repeated trials are impractical. That applies to structural reliability, where it is impossible to construct an identical building many times in order to see how many times it fails. Bayesian statistics encompass classical statistics but allow the incorporation of subjective information. As a result, the probability is interpreted as a degree of belief. This approach means that the probability is subjective and influenced by the knowledge of the engineer who assigns it. The next slide addresses the fact that we have already used the word event in this video. For example, we have talked about the probability of an event, such as a failure event. For this reason, we must learn to work with events before we can calculate the probability of such events. Formally, the language we use when we work with events is called set theory. Venn diagrams is a technique for visualizing events. Two Venn diagrams are shown on this slide. One is discrete, on the left-hand side, and one is continuous, on the right-hand side. The set of all possible events is called the sample space. S. Each individual sample point is denoted by X. Any collection of sample points is called an event, generically denoted by the symbol E, perhaps with a subscript to further identify the event. The next slide defines the concept of a complement. This Venn diagram shows that the complement of an event, E, is every other possibility except the event E. Notice the horizontal bar on top of the symbol. In order to denote it as the complement of E, the symbol S was used on the previous slide as a notation for the entire outcome space of possible events. This is called the certain event. The complement of the certain event is the so-called null event. The null event contains no sample points and has no possibility of occurring. Naturally, S is then the complement of the null event. The next slide introduces two operators called the union operator and the intersection operator. These operators are used to create compound events out of two or more basic events. The union of two events, denoted with a U symbol, is an event that contains all the sample points that are either in E1 or in E2 or both. It is pronounced with the word or, so here you can say E1 or E2. Notice that the overlap region where both E1 and E2 occur is included in the union operation. The intersection of two events, denoted with the upside-down U symbol, which can actually be omitted in shorthand notation when we mean intersection, is an event that contains all the sample points that are in both E1 and in E2. It is therefore pronounced and, so here we can say E1 and E2. For a continuous sample space, the union and intersection operations are gray shaded in the Venn diagrams on this slide. The next slide gives an overview of the rules that apply to the union and intersection operators. The commutative rule says that the order of the events is not important. Notice in blue the shorthand notation for intersection. The associative rule says that the union of E1 and E2 and E3 is exactly that, regardless of whether you isolate some of the operations with a parenthesis. Notice again in blue the shorthand notation for intersection. The distributive rule is similar to how we multiply a number into a parenthesis that contains a sum in mathematics. For example, here the intersection with E3 is applied to each of the events E1 and E2 that appeared in union inside the parenthesis. The next slide introduces a phrase that you will hear in probabilistic analysis. Mutually exclusive and collectively exhaustive events means that the events do not overlap and that they cover the entire outcome space. Remember, for subsequent slides, that two mutually exclusive events means that the two events do not overlap. In other words, there is no intersection for two mutually exclusive events. We have one more slide to review before set theory, which is the language of events, is introduced. The two rules developed by De Morgan have a rhythm when you read them out loud. The complement of a union is the intersection of complements. Similarly, the complement of an intersection is the union of complements. These rules can be proven by considering Venn diagrams. The events on both sides of each equal sign are shaded in red on this slide in order to illustrate what the expressions mean. It is the fact that both sides of each equal sign is identical to the red shaded areas that prove De Morgan's rules. One example of the use of De Morgan's rules is to transform a parallel system problem into a series system problem, and vice versa. We consider such systems in the system reliability portion of structural reliability. Having learned the rules of events, we are now ready to learn the rules of probability. The concept of probability was invented in 1654 in letters exchanged between Blaise Pascal and Pierre de Fermat. At that time, they addressed problems related to gambling, posed by a local writer. probabilities were rarely utilized beyond gambling activities until the 1812 work by Laplace. However, we must turn the clock all the way forward to 1933 before Kolmogorov established the formal mathematical axioms that underpin the probability theory we employ today. The axioms of probability essentially state that a probability is a number between 0 and 1, and that the probability of the union of mutually exclusive events is additive. The understanding of that last axiom is reinforced in the Venn diagram shown here. These two events cannot occur simultaneously, illustrated by the fact that the two areas do not overlap in the Venn diagram. This means they are mutually exclusive. The third axiom of probability theory states that we can simply add the probability associated with each of these events in order to determine the probability of the union. For example, for two mutually exclusive events E1 and E2, the probability that the E1 or E2 will happen is the sum of the probability that each of them will occur. The axioms are by definition the rules of probability that we accept without further proof. The next slide proceeds to the first of several rules of probability that we prove with the axioms as a foundation. The probability of the complement of an event is 1 minus the probability of that event. This rule is derived by combining the second and third axioms of probability in the following manner. First, we use the third axiom to say that the probability of the entire outcome space, which is the union of the event E and its complement, is the sum of the probability of E and the probability of the complement of E. Next, we use the second axiom to say that the sum is equal to 1. In the end, we solve for the probability of the complement in order to prove this rule of probability. The next slide shows a simple example of using that probability rule. Suppose you know the probability of failure of a facility during a specific time period. What is the probability that the facility will be safe during that time frame? The answer is 1 minus the failure probability. The next slide introduces the union rule. This rule provides the probability of the union of two events that are not known to be mutually exclusive. This rule is justified by visualizing the two events in a Venn diagram. Unless the last term in the union is subtracted, namely the intersection event, then that red shaded area will be counted twice when we sum the probability of E1 and the probability of E2. The union rule is generalized on the next slide to more than two events. This version is called the inclusion-exclusion rule. There is a rhythm in the plus and minus signs on this slide. If we think in terms of a Venn diagram, we first add regions, then we subtract overlap regions, and then we add back the double overlap region that were subtracted too many times. The inclusion-exclusion rule plays an important role in system reliability analysis, which we will see in the short course on structural reliability posted at terje.civil.ubc.ca. Toolbox. The union of three events shown on this slide is in essence a series system. That means the failure event for the system is defined as the failure of any or all of the individual failure events. Next, we address the conditional probability rule. Importantly, a conditional probability is written with a vertical bar. A conditional probability like this one is read out loud in the following manner. The probability of E1 given that E2 has occurred. Or, equivalently, the probability of E1 given E2. Notice that the vertical bar means that you get a phone call, let us say, which gives you the information that E2 has occurred. It is no longer uncertain whether E2 will occur or not. The probability of E1 is now a conditional probability, conditioned on the fact that E2 has indeed occurred. The conditional probability rule states that the conditional probability of E1 given E2 is the probability of the intersection of those two events divided by the probability of E2. This rule can be justified in several ways. One approach is to think of n repeated experiments in which the events E1 and, or E the second of may occur. Suppose n2 is the number of times that E2 occurs, while n12 is the number of times E1 and E2 occur simultaneously. Then, employing the frequency notion of probability and letting the number of experiments, n, become large, the fraction from the right-hand side above is expanded as shown in the right-hand side at the bottom of this slide. According to the frequency notion of probability, the last term in this last equation is a probability in its own right. It is the number of realizations of E1 and E2 over the total number of realizations of E2. In other words, the sample space has been changed to include only outcomes in which E2 occurs. That change in sample space is one way to derive and understand the conditional probability rule shown at the top of this slide. The multiplication rule follows directly from the conditional probability rule. Here we simply solve for the intersection probability as shown here. An example using the union rule and the multiplication rule is shown on the next slide. The two Venn diagrams shown here have red dots, green circles, and a blue frame. That is because we here want to study the potential failure of two bridges, shown with red dots, subjected to earthquake damage if the epicenter of the earthquake occurs within the green circles. The epicenter can occur anywhere within the blue rectangle. This means that we are mixing the concept of a Venn diagram and a regular geographical map in this example. That is usually not a good idea, because it requires information about the distribution of probability density within the Venn diagram. It also requires more care when scaling the geometrical shapes in the Venn diagram than what is applied on this slide. Nonetheless, we adopt the geographical map interpretation in this example for illustration purposes. First, consider the Venn diagram on the left-hand side. In this case, the bridges are so far away from each other that, if one bridge is damaged, the other is not. In other words, the events E1 and E2, which indicates damage of each of the bridges, are mutually exclusive. The question we ask on this slide is what is the probability that E1 or E2 will occur? That is shown with the union symbol near the top of the slide, where we have also been given the probability of damage for each individual bridge, which is 10%. In the case where the damage events are mutually exclusive, the third axiom of probability theory suggests that there is a 20% chance that Bridge East 1 or Bridge E2 will get damaged in the impending earthquake. This is a large probability in a rather simple example that does not provide much additional information compared with the information that was given. Perhaps one insight can be mentioned for so-called series systems, where the failure of any component implies failure of the system. The result obtained here shows that the system failure probability can become large if the individual failure events are mutually exclusive. Now, let us have a look at the Venn diagram on the right-hand side. This is a situation where the two bridges are so close that they both may get damaged in the earthquake. The information given is that there is a 50% chance that one bridge is damaged if the other one is. The question is the same as before, namely, what is the probability that Bridge 1 or Bridge 2 will get damaged? The answer is given below the Venn diagram in the form of the union rule, which is an extension of the third axiom of probability utilized earlier. The union rule requires the intersection probability of E1 and E2. That probability is not given. However, we can use the multiplication rule to determine it because we have the conditional probability of E1 given E2. That is done here at the bottom of the slide, showing a 5% chance that both bridges will get damaged simultaneously. Substitution of that value, shown in orange, into the union rule, gives a 15% chance that Bridge 1 or Bridge 2 will get damaged. Following up on a previous comment, we can say that the series system failure probability will go down with the amount of overlap between the individual failure events. Next, we address the probability rule developed by Thomas Bayes. It was presented at the Royal Society in London in 1763, 2 years after the passing of Thomas Bayes. It was published in a paper the following year. This rule is employed to update the probability of an event, given some information. Suppose E2 is an event that is known to have occurred. Bayes' rule states that the probability of the event E1 in light of this information is as shown at the top of this slide. This rule is derived by starting with the conditional probability rule and adding the multiplication rule, which is done at the bottom of this slide. Bayes' rule is the foundation for an entire discipline within statistics, which employs a particular terminology. The probability of E1 is called the prior probability, because it is the probability of E1 before the new information becomes available. The probability of E1 given E2 is called the posterior probability. The numerator in Bayes' rule, namely the probability of E2 given E1, is called the likelihood and plays a central role in Bayesian updating. The likelihood is the probability of observing what was observed, in this case E2, which requires a model that says something about the connection between E1 and E2. Finally, the probability of E2 in the denominator of Bayes' rule often requires the use of the rule of total probability, which is addressed next. The rule, or theorem, of total probability has many applications in probabilistic analysis. It shares with Bayes' rule that it is often applied to random variables, which is addressed in another video. In this video, we limit ourselves to the probability of events. The rule of total probability provides the probability of an event that we know only conditional probabilities for. In this case, the main event is denoted by the symbol A. The assumption is that we have the conditional probability of a given several events denoted by EI. We also have the individual probabilities for E1, E2, etc. The rule of total probability says that we can multiply those individual probabilities with the corresponding conditional probability, and sum to obtain the probability of A. Importantly, the event A must be conditioned upon events EI that are mutually exclusive and collectively exhaustive. The rule is derived as shown at the bottom of this slide. First, we consider the intersection between the event A and the entire outcome space. Next, we recall that the outcome space consists of the events EI because those events are mutually exclusive and collectively exhaustive. Next, we apply the distributive rule for working with events. In a sense, we multiply the event A into the parenthesis that contains the union of the EI events. Next, we apply the third axiom of probability to sum up the individual probabilities. We can use that axiom because these events are mutually exclusive. Finally, we use the multiplication rule to substitute the intersection probabilities with the product of the conditional probabilities for A times the individual event probabilities. It is important to remember that the events EI must be mutually exclusive and collectively exhaustive before you can apply this rule of probability. Another way to say that is to demand that the sum of the probability of all events EI must add up to 1. Let us now look at an example of using Bayes' rule, where we will see that the rule of total probability is needed. We consider the manufacturing of a wood product that comes out of the factory as individual specimens. Unfortunately, some of the specimens are flawed. We let the symbol F denote the event that a specimen is flawed. Fortunately, we have a testing device to help us understand if a specimen is flawed. The symbol D is employed for the event that the testing device detects a flaw. Based on experience, 0.8% of the overall population of specimens are flawed. The test device is not perfect, but there is a 90% chance that it will detect a flaw if a flaw is indeed present. On the other hand, there is a 7% chance that it will raise a flag even if there is no flaw present in the specimen. What is the probability that a product that is identified as flawed in a test is actually flawed? It turns out that Bayes' rule can address this question. That is because we are working with the probability of a specimen being flawed in a situation where new information is coming to light, in this case a test result. Looking at Bayes' rule in this case, we already know that the probability of detecting a flaw when a flaw is present is 90%. We also know the prior probability that a product is flawed, which is 0.8%. However, we do not know the probability of detection, which appears in the denominator. The rule of total probability comes to rescue. Notice that the event F and its complement are mutually exclusive and collectively exhaustive. Also notice how we evaluate the sum dictated by the rule of total probability. The probability of the complement of F is 1 minus the probability of F, as we learned earlier in this video. After substituting the result from the rule of total probability into Bayes' rule, we find that the probability of a flaw is less than 10%. This may appear puzzling, because the test device just raised the flag for this specimen. This is like going to the doctor to take a test, with the test coming back positive. The probability of actually having the condition that was tested for may still be small, like 10% in this case. This is one reason why the modern medical doctor is trained in the understanding of Bayes' rule. A major contributing factor to the result obtained in this example is the prior probability that a specimen is flawed. With only a 0.8% chance of a flaw, in general, the probability of a flaw remains quite low even after one positive test. Next, we address an example that involves a facility subjected to earthquake ground shaking. The symbol F denotes the event that the facility fails. The ground shaking can be strong, moderate, or weak, denoted by the symbols S, M, and W, respectively. The information is given that moderate ground shaking is 3 times more likely than strong shaking. Also, weak shaking is 3 times more likely than moderate shaking. The probability of failure of the facility given different ground motion intensities is also given. First, we ask what the failure probability is. The information that is given does point to the use of the rule of total probability to obtain the answer. However, we must be careful when entering the probability values for strong, moderate, and weak ground shaking. That is because the rule of total probability can only be applied when the individual events are mutually exclusive and collectively exhaustive. In other words, the probabilities must add up to 1. That is ensured by the calculations inside the framed box on this slide. Notice how the information about the relative likelihood of different types of shaking is used in order to normalize the probabilities so that they sum to 1. The individual probabilities are shown with blue, red, and green colors. After evaluating the rule of total probability, we find that there is a 3.5% chance that the facility will fail, considering all possible shaking intensities. At the bottom of this slide, we ask another question. What is the probability that the earthquake was strong if the facility got damaged? After sifting through the collection of probability rules, we find that Bayes' rule may answer the question. We have the probability of failure given strong shaking. We have the prior probability of strong shaking. And we have the denominator in Bayes' rule, namely the probability of failure, from the earlier calculation in this example. The result is a 65% chance that the failure was caused by strong shaking. Finally, we address the concept of statistical dependence. 2 events are said to be statistically independent if this equality holds true. In words, the 2 events E1 and E2 are independent if the probability of E1 given E2 is the same as the probability of E1 without any information about whether E2 has occurred or not. It is equivalent to check whether the probability of E2 given E1 is the same as the unconditional probability of E2. Notice that this is the only definition of statistical independence. There is no other way to check whether 2 events are independent than this definition. A consequence of statistical independence becomes clear if we substitute the conditional probability rule on the left-hand side. We then see that a consequence of statistical independence is that the intersection probability of E1 and E2 can be obtained by multiplying the 2 individual probabilities for E1 and E2. This only works if the events are independent. It is not particularly meaningful to visualize statistical dependence in a Venn diagram. However, the diagrams at the bottom of this slide are included to make the following point. The events in the diagram on the left-hand side are most definitely dependent. That is because, if we receive the information that one event occurred, namely that the outcome is somewhere inside one of these circles, then the other event guaranteed did not occur because the events are mutually exclusive. In this case, there is no way that the 2 events can pass the test of independence at the top of this slide. Conversely, the diagram on the right-hand side show events that may well be independent. If we receive the information that one of the events have occurred, then there is still a possibility that the other event did also occur. The intersection probability may be exactly such that the test of independence at the top of this slide is passed. Here is an example where we check for statistical independence by calculating numbers. There are 3 pipelines crossing an earthquake fault line. If an earthquake occurs along this fault line, then it is assumed that the rupture is 30 kilometers long and that it can occur anywhere along the fault line with uniform probability. Notice that the full 30 kilometers rupture, shown in red, must occur inside the boundaries of the 150 kilometers fault line, shown in blue. Are the failure of the pipeline statistically independent? To answer that question, we must compare the probability of failure of each pipeline to the probability of failure of one pipeline given failure in another pipeline. This example allows us to determine probabilities by geometrical considerations. Consider this fraction. The numerator is the range of outcomes, namely the range of locations of the rupture, that will cross a given pipeline and therefore cause it to fail. The denominator is the length of the full outcome space. Notice that we must subtract 30 kilometers from the full 150 kilometers length of the fault line because no portion of the rupture can occur outside the fault line. The result is a 25% chance of failure of any given pipeline. Carefully note that it is not possible to determine the conditional probabilities by geometrical considerations. Instead, we aim for the intersection probabilities. The probability that both pipeline 1 and pipeline 2 will fail simultaneously is calculated here, in the same manner as above. The probability that both pipeline 1 and pipeline 3 will fail simultaneously is calculated here. The probability that both pipeline 2 and pipeline 3 will fail simultaneously is calculated here. We now utilize the conditional probability rule to determine the conditional probabilities that we need for the independence check from the intersection probabilities that we just calculated. The result shows that the conditional probability of failure of pipeline 1, given failure of pipeline 3, is exactly the 25% chance that was calculated for the individual pipelines. This means that the distances given in the figure at the top are exactly such that the failure events for pipelines 1 and 3 are statistically independent. In other words, if you receive a phone call immediately after the earthquake, telling you that pipeline 3 has failed, it does not affect the probability that pipeline 1 has failed. That is the meaning of those events being statistically independent. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.